Imagine your application suddenly gets 10 times more traffic. Your server CPU is maxed out. Requests start timing out. Users can't log in. At that moment, upgrading the server isn't enough. You need to scale beyond a single machine. So how do modern systems handle that? Let's look at multi-node architecture. Most applications begin with a single server. That server runs the application, handles incoming requests, and communicates with a database. For smaller systems, this works perfectly well. But as traffic grows, the workload increases. More users mean more concurrent requests. Eventually, the server reaches its limits. CPU becomes saturated. Memory usage increases. Network bandwidth becomes a bottleneck. At that point, upgrading the machine only helps temporarily. Sooner or later, the system needs a different strategy. Instead of scaling vertically by making one server stronger, we scale horizontally by adding more servers. This is known as multi-node scaling. In a multi-node architecture, multiple machines run the same application. A load balancer sits in front of these servers and distributes incoming traffic. From the user's perspective, everything still appears as a single system. But behind the scenes, multiple servers work together to handle requests. The architecture typically looks like this. Clients send requests to the load balancer. The load balancer forwards each request to one of several application servers. Each server processes requests independently. Because traffic is distributed, the overall system can handle much more load than a single machine. However, introducing multiple nodes creates new challenges. One of the first problems that appears is session management. Imagine a user logs into your application. If the session is stored in memory on server A, the next request from that user might reach server B, but server B has no knowledge of the session stored in server A. This can lead to authentication failures, lost sessions, or inconsistent behavior. One way to address this problem is sticky sessions, also known as session affinity. With sticky sessions enabled, the load balancer ensures that a user's requests always go to the same server. If the first request goes to server A, all subsequent requests from that user continue going to server A. This allows session data to remain stored in that server's memory. While this approach can work in smaller systems, it introduces several limitations. Traffic can become unevenly distributed. One server may become overloaded while others remain underutilized. And if that server crashes, all session data stored in its memory is lost. Because of these limitations, modern systems usually avoid relying heavily on sticky sessions. Instead, session state is moved outside the application servers. Session data is stored in a shared system, such as Redis or a distributed database. Now every server can access the same session information. It no longer matters which server handles the request. Any server can process it. This makes the system easier to scale and more resilient. This leads to another important principle in distributed systems: stateless services. A stateless service does not depend on local server memory to maintain user state. Instead, each request can be processed independently. All persistent state lives in shared infrastructure such as databases or distributed caches. Stateless systems scale naturally across multiple machines. They also improve reliability. If one server fails, another server can immediately handle incoming requests. Another key component of multi-node systems is the load balancing strategy. The load balancer decides which server should receive each request. Different strategies can be used. Round robin distributes requests sequentially. Least connections sends traffic to the server with the fewest active connections. Weighted distribution allows more powerful servers to handle more traffic. Modern cloud platforms often provide managed load balancers that implement these strategies automatically. Multi-node systems must also handle failures gracefully. Servers can crash, networks can fail, infrastructure can become temporarily unavailable. Load balancers typically perform health checks. If a server becomes unhealthy, the load balancer stops sending traffic to it. Requests are automatically routed to other available servers. This improves the overall reliability of the system. As systems grow larger, monitoring and observability become essential. Logs, metrics, and traces must be collected from multiple machines. Centralized monitoring systems allow engineers to observe behavior across the entire infrastructure. Without proper observability, debugging distributed systems becomes extremely difficult. So let's summarize. Scaling inside a single machine uses multiple processes across CPU cores. But eventually, systems must grow beyond the limits of one server. Multi-node architecture distributes traffic across multiple machines using a load balancer. Session state moves into shared infrastructure. Services become stateless and interchangeable. And the system scales simply by adding more nodes. When one server isn't enough, horizontal scaling becomes the foundation of modern backend systems. If you're interested in understanding how modern software systems actually work, subscribe for more deep technical breakdowns.